Hi, I will explain to you how to set up, calibrate and operate this AC volt amp meter known as the AEG Vektormesser II. Well, first of all, please note this is rather a big machine compared to a standard handheld multimeter. Look the difference in size. This is not a small one, and look to the size difference with the Vektormesser II. This Vektormesser II is rather unique. You might think, wow, we have many volt amp meters, but this works a little bit different. Let's go through the buttons first. Like any volt amp meter, it has range function set up for voltage and for amp. So I can set my expected amp and voltage. I have separate terminals to bring in the voltage, they are here, and for the amp meter connection. So I don't need to switch wiring, I just can, with this button, go between volts and amps. That's nice. There is also one here. One means going directly to the instrument without the shunts and the series resistors, so there are inputs 1. We will not use them today. What makes this meter unique is the following. It's an AC volt amp meter using, as you can see there, a galvanometer, which is only working on DC, so it needs a kind of rectifier, and normally we use diodes, selenium or whatever, germanium, but this mentions it's using a switch for rectifying. By the way, also notice the high precision of this instrument. It's from 9055 and it says 0.5%, which is quite high for that time. So we need to use it horizontally, and the test voltage for isolation is 2 kilovolt. Okay, what does this mean? Also, the name Vektormesser II, which you can translate as vector meter number 2. So there was a number 1 before, yes. So what is this rectifier? Well, this rectifier is done mechanically by a synchronized switch, which is driven by a little motor, and you can see the system here. Later you will see it working. Now it's still off because the meter is not connected. By the way, the glass is broken. It was broken when I bought it, but that is not so bad because I could buy it for a very low price. So, but there is a little contact that will open and close under the action of the little synchronized synchron motor. Let's see the rest of the instrument. Here there are buttons. I will explain later. This is a calibration button for the battery and the phase button. Then here there is a plus minus, which we can change from plus to minus if the instrument is going the wrong way. This is TK, this is Kalibrierung, which is calibrating in German. Jawohl. So, and that's not all, because, at the backside, the instrument needs 220 volt. I'm in Belgium, Europe, so here it's 220, and these are direct outputs from the instrument. Maybe we will use them, and at the back side we see some explanation diagram of the internal of the unit and different connections mode, because the synchronized rectifier you can set in series with the instrument or in parallel, and then you can also go to an external equipment. If you don't want to use the internal meter, you can go to an external, maybe more accurate meter. Then you have to connect otherwise. Also behind this door is a battery, 4.5 volt battery that we will need for the calibration. Okay, so the instrument needs 220 volt. Why does it need 220 or 230 nowadays? To make this little motor run. So if I connect (220), there is no power yet, don't worry. And I will also prepare the voltage measurement. Oops, I prepared the cables a little bit to advance quickly. So now I connected the 230 for the synchro motor, the voltage to measure the voltage. It's the same voltage. We're just gonna measure the mains, and this here we will measure current. As a load, I just have a transformer. Transformer is an inductive load. You will see why. Okay. Looks what happens if I power the instrument. The motor starts to turn. I'll shut it down, you can see, and open and closes this little contact. You see? Also, I can rotate the disc. Since it's a synchronized motor, and since I can change the position, I can change the phase of the opening and closing time of the contact, which means I can measure several things of my incoming waves. I do not just detect, but I can decide which portion of the incoming sinus I will measure. It's like a sampling circuit. I can scan the whole thing. And it means I can use it to detect phase difference between voltage and current. So I can measure cosinus phi, or the power factor, with it. And I can also analyze for higher harmonics if I want. But let's just set it up and calibrate the instrument before we can use it, because the opening time of the contact must be carefully set. Normally, when we do a normal measurement, we will take 1/2 of the period, so 180 degrees must be the exact closing time of the contact. How can we get to there? Well, they found a very genius way to do so by using an internal battery and by using this calibration function. If I push this button, the instrument goes out. It's now driven. There is no current on this equipment. I can set current, but it's not needed. I just feed DC to my instrument, and it must go to 90 on this pointer by using this potentiometer. So I set it perfectly to 90. And that is the reference of my battery. Now I make the instrument run and go to the second position of calibrating. I rotate the button and release it. There we go. And now I set, here with this dial I can adjust the closing time of the contact, and since it must be 180 degrees, and since I'm working on the battery which is delivering 90, the pointer must indicate 45 if we are on 50% contact time, 180 degrees. So I go now to 45, and that is the end of the calibration. So now I set this as normal, and now the unit is ready to work. Well, it's not ready 100% because this dial I can rotate, and we have to find first of all the maximum of this sinus. It's very difficult to find the maximum of a sinus because it's flat, the slope is flat, so we will not find one point. So it's much better to find the zero crossing because the slope here is very steep, and that's what they suggest to do. So we set here 0 degrees. The instrument is not indicating 0. Then we have a phase adjustment here, and we set the instrument to 0. I can go to a more lower level to be more sure about the 0. Let me show you in detail. We really go to 0. There we are. Okay, we set back to 300 volt because we expect something like 230. Now, because we are now scanning this period and the average is 0. So if we want to measure this portion, we need to move the synchronized rectifier to 90 degrees in advance. Since the motor is spinning that way, advance means going that way. So if we go 90 degrees in advance, which is the end also of the dial, we can measure our voltage. So we are on 300 volts, this reading times 2, so we have 200, almost 240 volt. And I checked it with the digital multimeter. It's unbelievably accurate. Now we want to measure the current by this little taken by this little transformer. So we change the dial to to amps. We go back to the 0 position because we do not only want to measure the current, we also want to know the phase difference. Since this is an inductive load, the cosinus phi will not be 1. So I first bring it into the region I want, and then, as you can see, this is the voltage. This is where we measure the voltage. If I go to amps, it becomes negative. That is normal because it's an inductive load, so the current will be lagging behind. So I go to negative. Okay. Now I look for the maximum. As you see, the maximum, because the top is flat, we can find not only 1 point. Okay, but the maximum and the current is about, so this is 150 milliampere. So 150 milliampere full scale. So this transformer at this moment is taking about 66 milliamps. Now I want to know the cosinus phi. Therefore, I need to find, this is back on my 0 in the middle of the dial. So here, we are there. So now we're going to shift and look to find the same point for the current. So I switch back to current and I look where I found the 0 point for the current. Okay, there we go. Oops, negative now. No, we want 0. 0. I go to more sensitive range just to find the 0 better. There we are. So we can see we started from 0 degrees, that we are about on 60, 70, 75, 77 degrees. Wow, this load is very inductive. And yes, on the other side we see the cosinus phi, or the power factor, which is about 0.2. That is nice. By the way, to close, this instrument also has an output of the meter system. So if I connect that to an oscilloscope, we can really see the instrument. We can see the sample rate. So here B and C are outputs, and I prepared a scope. Yes, power on. Now, if I start the instrument again, there we are. You can see this is the 0 position of the dial. You can see it's really sampling out. I reversed the connection, but that's not so important. I sample really out. Oh no, this button is still on negative, that is why. I really sample out half of the sinus. Then if I move on, I take the positive or the negative, and you can really see it is a very nice 180 degrees. There is no overshoot, undershoot or whatever. So he really takes the mechanical contact is taking really, when it's nicely calibrated, 180%, so half wave of our sinus. Thank you for watching.